Welcome to cold and gloomy Toronto, home of Toronto MetRobotics. Over the past 9 months, we've put into motion developments and strategies that we learned from competing at URC last year and discussing with our fellow competitors.
We took those lessons back to the workshop, challenged our assumptions, and pushed each sub-team to improve. The result is a more refined rover and competition-ready team.
This year, the mechanical team's main focus is the implementation of our brand new 6-degree of freedom arm. With 4 custom cyclotron actuators and 2 direct drive motors, this arm has a work envelope of a cubic meter. Each actuator produces a compound 78-to-1 reduction, using a split housing to fit 2 stages of cycloid disc in the form factor of a single stage with little to no backlash. As our 6-DOF arm is still in development, we are proceeding with testing of our software systems on our previous 5-DOF arm. Interchangeable adaptive and parallel end effectors are attached, each capable of 300 newtons of clamping force, with compliant grip pads. Manufacturing sheet metal brackets as part of their designs allowed for a lightweight improvement to both claw precision and structural integrity.
To minimize points of failure and reduce the overall weight of our rover, we have opted for a unibody chassis design. With the implementation of seam welding, we were able to ensure that strength characteristics and rigidity were maintained. Our updated drivetrain has further reduced rover's weight by 3 kilograms to ensure our total weight stays below the 50 kilo maximum. This is achieved through new spoke-supported wheels and printed TPU tires that greatly simplify the manufacturing process without compromising on shock absorption and traction.
This year, the software team has focused heavily on improving the reliability and maintainability of our systems on the rover. Our control system has been redesigned using SDL2 for its cross-platform support and standardization of controller inputs. This allows us to run our code on multiple operating systems using X-input and direct input controllers. Communication is established using ROS2 messaging by default, with the ability to switch to custom UDP packets to maintain control of our rover under unstable network conditions. To accommodate the rover's new arm, we have moved away from using our custom inverse kinematic solver from last year to the open source Move It 2 package, leveraging its reliability, motion planning features, and ROS2 functionality. For the autonomous mission, we have improved our rover's object detection capabilities using a combination of real-world images and synthetic data generated through our custom Blender simulation pipeline. This allows us to quickly generate datasets and simulate objects in conditions similar to the competition environment.
The autonomous team has also fully integrated Nav2 into our system, improving navigation and obstacle avoidance by using point cloud data from our Z2S stereo camera to generate local cost maps, allowing the rover to perceive obstacles in 3D. Furthermore, a new IMU device has been integrated into our system and fused with existing sensor data through an unsetted Camlin filter, resulting in improved rover localization and centimeter accurate positioning. For our camera system this year, we are able to stream 6 feeds simultaneously at any given time using H.264 encoded video over UDP with GStreamer to minimize latency and reduce network overhead. New features include scale indicators to support the science mission, as well as a replay buffer to save and review the last few seconds of footage during critical moments.
This year, the electrical system is upgrading to a 6S battery, creating a scalable and flexible system for major upgrades such as stronger, more efficient motors. The battery is accompanied by a custom voltage monitor built into the casing, which monitors each cell's voltage and cuts power should the voltage fall below the acceptable threshold for a prolonged period.
To facilitate the battery upgrade, the power system will also have a custom-built voltage-selectable buck converter, which will be able to connect through a backplane or wired connection. This creates a flexible power system able to support pre-existing components alongside any ad hoc power needs.
This year, we are switching our brushless DC motor drivers to the O-Drive S1. These drivers allow us to have precise control over movements thanks to field-oriented control. This makes the S1 the perfect choice for speed and precision applications. Additionally, the S1 offers a flexible solution for a wide variety of 3-phase motors.
This year, the science team focused on enhancing the science console, which is capable of conducting in situ analysis to assess the potential for life and habitability across multiple test sites. For live detection, we implemented the improved version of last year's lipid assay. This updated protocol uses Nile blue staining along with chloroform and vanillin for effective extraction and solubilization of phospholipids and hopanoids respectively. UV-vis spectrophotometry measurements are then taken at 540 and 650 nanometers to calculate the phospholipid to hopanide ratio in the sample. In addition, we designed a custom 3D printed ion probe array to detect key ions such as potassium, calcium, and hydrogen. This system plays an important role in evaluating soil chemistry and overall habitability. To further support the mission objectives, our upgraded camera system captures high-resolution panoramic images of the test site, which supports stratigraphic profiling and includes a digital microscope for visual analysis of geological samples.
This year's soil collection system features a high-torque hammer drill to break up packed soil, allowing for effective sample extraction below 10 centimeters. The collection module has been shifted further into the chassis, leveraging its weight to drive deeper into packed soil. To measure soil conditions, our new temperature and moisture sensor is mounted parallel to the auger, working in tandem with this collection process. Upon collection, the samples are loaded into our dual distributor system, which splits the soil into 2 separate carousels. Each carousel houses multiple test tubes for lipid assay and ion probe testing, as well as a self-closing cache, which will be submitted to the judges. After distribution, the samples are transported into the testing sites on the rover using our new peristaltic pump multiplexer.
As we prepare for competition, our team is dedicated to rigorously testing and refining our rover systems to ensure a high-level performance.
We are incredibly grateful for the continued support of our sponsors, without which this project would not be possible. Thank you for watching our systems acceptance review. We are looking forward to showcasing our hard work at URC.